Hello. My name is Alin, and I'm here to present to you about how Bitcoin's expansion into DeFi brought with it a lot of security assumptions at layered and new trust models. A very quick bit about me. I worked in cybersecurity as a malware analyst for 8 years in Bitdefender. I then went into DeFi and smart contract auditing, and over the years, I've specialized in Bitcoin L2s, mostly stacks, going into the other ones, and made my own company at one point. So I'm here in the long run, and I will secure as long as I am here. Okay, I'll start off with Bitcoin core assumptions. For what we use Bitcoin, but from a security point of view, we need to presume and have some assumptions. We assume that this chain works by specific trades and rules. I listed here 7 assumptions which are more relevant to an interaction with Bitcoin. These are pretty straightforward. The first one is that honest majority of hash power. We all know the classical 51% attack, where you say that an attacker controls more than 51% of the network, and proof of work, they can decide it. We're always interacting with Bitcoin presuming that the current majority are honest. This is a normal assumption. The cryptographic primitives, again, we're presuming that they will hold, but these are like low-level ones. We're literally presuming that SHA-256 doesn't break, or the elliptic curve algorithm doesn't break. We have such assumptions. Now, I'm presenting these because I want to add the following rhetorical question. Over the years, how many of them do you think have actually been broken historically? I mean, they're not broken now, but over the years, they have been broken. And to answer, actually almost all of them, especially just the first 2, they haven't been broken. The other ones have, at one point in the existence of Bitcoin, have been broken in one way or another. We'll go quickly through them. The one that consensus rules are correctly implemented. This is from a code point of view, that the node implements the software correctly. This was actually broken in 2018 when a bug allowed to have double inputs validation, which means that you could have minted more Bitcoin that existed. This was the most severe bug in Bitcoin at that time. Also, a bit of side of an information. You see here CVE. In security, we usually assign ID to more relevant bugs called common vulnerabilities and exposures. That's more of a fancy way to allow the public to know what vulnerability, instead of giving it fancy names like Heartbleed or Dirty Cow or other media and PR designations. So that's just an ID. Now, network liveness. There have been over 19 denial of service error vulnerabilities in the Bitcoin node software up to today. That means that at one point, at 19 different points, the network could have been blocked partially, nodes could have been stalled, transaction liveness was at risk. Now we're interacting with Bitcoin, hoping and expecting it in about 10 minutes, give or take, a transaction to be minted. That's our assumption. Again, we have assumptions about everything we're using. The node integrity is that we're presuming simply that the software that runs it is not malicious and cannot execute malicious code. There were 3 cases of potential remote code execution, the RCEs, in which one was actually almost confirmed. You could have executed malicious code on the node software. Again, bugs introduced but were fixed and resolved. But it did break for a short while the invariant, just what we were expecting. Coming back to the example of the consensus implementation break, the same bug introduced allowed more than 21 million Bitcoins to be minted. We know how everyone says that, hey, Bitcoin has a fine cap. Yes, it does, but that wasn't implemented correctly at one point. Actually, for 2 versions, I believe it was a problem. Oh. Either way. Now, the last one is a bit interesting, the canonical source of truth. We're presuming when nodes and anything interacting with Bitcoin presumes that Bitcoin is the source of truth, and we look at it and it's okay. Whatever we see it is the valid state, but there were 2 issues of bugs and vulnerabilities that allowed software to see different versions at the same time. So that assumption that what we're looking at is valid would have been different. You had a different output depending on who was watching it. This is, again, a critical and a major problem. Imagine an exchange seeing a transaction done, but other exchange do not seeing it. You could have had double spending. Very interesting bugs, just mentioning them. Basically 5 out of 7. The other 2, which was honest majority and cryptographic primitives, well, if you break those, you break a lot. Well, if you break the cryptographic primitives, you break a lot of the internet. And the honest majority one, you kind of need incentive there, and no one has an incentive to do that. Overall, if we treat the Bitcoin software itself as like an audit report, we can see that there were 25 different vulnerabilities, and about, okay, 1 was critical, the 4%, 40% in mediums, and high and lows. These were all the issues over the years. Another interesting observation here. Okay, Bitcoin had issues, and they were disclosed, but the Bitcoin core team, since everyone is looking at Bitcoin, and if you see an issue there, they're gonna mass media it to as much as they can. They actually had quite a bit gap until when they found the bug, they fixed it, and they released, and they publicly disclosed it, like years. I mean, the only one that was almost instant was the critical, but that was 2018. Up till that point, you have an average over 2 years. I mean, if history holds, there could have been bugs now, critical ones, that have been fixed, and we'll only hear about them in 4 years. This is just a thing about assumptions and discussing it. It's an interesting observation. From what issues there were in BTC, DOS, denial of service, is vastly the majority of it. Now, you may be thinking, okay, denial of service, we're blocking nodes. At the most, we're delaying transactions. So that's fine. Well, that's not really fine. You can do a lot of things with the denial of service in a network. Depends on, maybe you're using it to leverage with a different attack. I'll give you a side quest, a side story about Litecoin and how a DOS helped attackers do a specific hack. Litecoin is a fork of Bitcoin, a software fork, not a blockchain fork as in they took the code in 2011, they added stuff over it. 2024, they added some random Mimblewimble extensions. I don't know how they got that name. And in March, they were hacked. That Mimblewimble extension added an inflation attack. That means that they could create infinite Litecoin. Okay, they fixed it, and it was silently resolved as a white hack operation, as in the attacker gave the money back, a part of it. Okay. They fixed it, but in April, it was hacked again. But this time, it was not a white hack operation, and it was a subtlety here, because what actually happened was they reused the same logic. As in, they created a malicious block, which the correctly patched nodes had an issue with it, and they were DOSed. The unpatched nodes, because you cannot really presume that the entire network patched the April one. Let's say there were like 5% of nodes. Those 5% of nodes became the majority, and they allowed the previously fixed inflation attack to still continue. So for half an hour, 13 blocks, until the devs at Litecoin patched the patched, there was almost 8 Bitcoin that were off-chained to near intents. There was some to on-chain, but like 10 Litecoin. This was very interesting, as in if the DOS would have not existed, then the correct patched nodes would have not had any issue. But it existed, the patch node that had a problem, and by the time the chain reorged, hey, off-chain swaps, cross-chain swaps, they remain, the money was stolen, and the near protocol ecosystem absorbed the loss, basically, because there is no counter on the Litecoin part. This was an example of issues that simply can appear due to a DOS. And I wanted to make this parallel because imagine if it was Bitcoin. Imagine that now you have a version, let's say, of the inflation bug node that still exists, and you find a DOS for the entire network and use that. You could still do something bad, as you can DOS parts of the network while using a bug on the other ones. You can create a lot of issues. You can spun up as a malware out of your own network while you're DOSing your own nodes while you're DOSing the other ones, but that's kind of costly. Either way, nodes, DOS is irrelevant, and every breakage to every assumptions can be abused. Now, I've discussed about Bitcoin and security assumptions that go into BTCfi. BTCfi is a fancy way of saying Bitcoin on DeFi, but you're combining it, saying BTCfi, basically using Bitcoin as an asset. Over the years, I mean, why do we want to do this? Liquidity. Liquidity is the main problem in any ecosystem today besides security, of course. And to fix it, we're looking what's the most liquid asset, Bitcoin. When I was making this presentation, it was $1.6 trillion, but BTCfi, according to DeFi Llama AI, something around 5.7 billion. So we're not even 1% of the entire Bitcoin market cap being used in DeFi to produce yield to actually help with something. So people will try to do this. They will invest a lot of money in this, and they want to do this and will do this one way or another. That means that we need to accept some assumptions and work around them. The BTCfi stack at this point, there are a lot of experiments, chains, and modes in which people are doing BTCfi. I want to go to 3 major categories. The self-existing smart contract layers like stacks, which is independent, its own ecosystem and all its own consensus, but they're anchored to Bitcoin. There are the ZK rollups that use BitVM type technology. I'll go into that a bit, to have the data availability layer on Bitcoin and have cryptographic primitives which allow it to show that the transaction was validated on chain. And another example is Babylon, which they're doing novel cryptography with a staking mechanism, each their own way. Of course, there are other L2s because everyone wants to be the next Ethereum, but for Bitcoin. So they're doing their own implementation. These are the majority. I mean, the majority of research is going into these at this point. Okay, overview of stacks. They're using something, there's an independent L1, considering as an L2 to Bitcoin because they have their own consensus, they have their own tokens, but they are anchored to Bitcoin. As in their transactions, the consensus mechanism binds a final output to Bitcoin. So you actually need to reorg Bitcoin in order to reorg them. It's pretty transparent from that point of view. They also implemented their own BTC native wrapper, which is called SBTC. And they're using a 70% threshold for 15 signers. Now, from a security point of view, what assumptions we have here? We have assumptions that 11 out of the 15 signers are trusted. So if they are not trusted, we have a theft. We also have an indirect assumption that if they're not online, 11 of them, funds cannot be moved from chain to chain. Again, we're using BTC, so we need to have some trust assumptions. This is one of them. And the proof of transfer, in case you didn't know this, proof of stake, proof of stamp, so proof of history, proof of liquidity, proof of whatever. Proof of transfer is not economically viable, MEV will appear and no one's going to use the chains. These are some assumptions on stacks. I want to go to Citrea, but before it, BitVM is one of the most interesting interesting mechanism being researched today. Basically, they're trying to compute verification on Bitcoin, but off-chain, they're doing as much calculations and cryptography as possible and just doing optimistic verification on-chain. They're putting some proofs and someone can challenge it, and the challenging costs, in order to challenge a BitVM proof, you are going to need, in this case, for BitVM type 2, for example, you need 1 gigabyte on Bitcoin, which is split into multiple transactions, so it's not actually feasible. Research has been done into this and has 3 versions at this point. BitVM 1 it was more theoretical. It required a bit like a month of off-chain calculations, so you can have one on-chain validation, because you need to do as much as you can off-chain and as less as you can on-chain. Very impractical. BitVM 2, there's actually 2 chains that have deployed this, and used this mechanism, Citrea and BitLayer. But it's kind of costly. And the BitVM v3 version, something that it uses garbled circuits, that's another cryptographic primitives in a way that you can show that you can validate, 2 parties can validate an outcome by their private inputs without showing them. It's somewhat odd, but they found that they can use that and have it on-chain, on Bitcoin, and be implemented as it is with the L1 itself. Remember, I'm talking about the L1 itself logic. Okay, so Citrea took that, implemented it, and they have. The trust assumption is very nice. It's basically 1 of n. You need only 1 challenger to be trusted, because everyone can put whatever they want, but 1 should be trusted because he's going to check, and if it's false, then he is incentivized to do that, and it invalidates the transaction. They implemented ZK EVM itself, so this is already EVM. Using the entire assumption tree from Bitcoin to BitVM, you already have an EVM compatible chain here that has native-ish Bitcoin bridging. In this case, we have, again, assumptions. The assumptions the ZK logic works. The verify itself is correct. The challenger liveness, I am incentivized by the fee to actually do this. There are, again, assumptions. The Babylon BTC staking logic itself, they're trying to, your funds as a staker are staked on Bitcoin using taproot time locks. So technically, they're still somewhat yours. You're deploying on for each of your staking, and they're using another novelty algorithm that again uses as little of a footprint on the Bitcoin chain itself, to ensure that the transaction of bridging the pegging out or in is valid. In this case, they also added a slashing mechanism, which again brings more assumptions. We assume that the novel algorithm is okay. We assume that the slashing is incentivized enough. They're calling operators finality providers. Either the operators, their challengers, their whatever, third-party entities, probably something working in AVS or whoever has a data center, whatever. The idea, they're presuming someone, they're naming it as such. Of course, the consensus should work. If we look at all of them, we see something interesting that I try to put them in such a way that from left to right, on left we have more trust in individual entities, and on right, we have more trust in the technology. So basically, on Stacks, we trust the bridging of 15 signers, honesty. On Citrea, we trust that the BitVM implementation goes further. On Babylon, we trust that their logic, but funds still remain there. We have how trust is defined, who holds the BTC, a multisig. Each of the challenger gives the multisig's worst cases and how you are disputing it. General entities and institutions try to not focus, try to reduce human entities as much as possible. Basically, the idea is going to technology as much as possible and not to individual entities. But there is also here, I have no idea which one of these technology will actually be the best. I know they're working on all of them. And each of them has its own assumptions, which bridge someone who uses it, institutions or banks or whatever, and they need to accept their own trade-offs. Again, as an overview, as I said, that we're talking about how you would bridge to Bitcoin to Ethereum or EVM ecosystems. We have a layered trust system. We are trusting that Bitcoin itself and its assumptions hold. I showed that some assumptions did not hold historically. Okay, now they're all holding up. We are trusting that the bridge pegging mechanism exists. We are trusting that the consensus mechanism exists. We are trusting that all of these, which stack one upon the other and up until the application layer, that they are all correctly implemented. Now, we as security researchers need to ensure all of these are actually safe. We try to ensure that nothing breaks, because anything that breaks anywhere compounds. And the more we are up in the stack, the more assumptions we have and the more space to hack, the more attack surface there is. Guess this is the key takeaways. Okay, Bitcoin has had bugs over the years. It's not a bug-free chain, and there probably still will be some bugs at one point. Relevant or not bugs will remain to see. All bugs compound upwards. So a bug in the base layer, Bitcoin itself, will reach the bridge and the EVM implementation itself. A bug directly in the EVM implementation that uses the bridge mechanism may only lose there. They're compounding. You cannot bypass it. By stacking layers, we stack more assumptions. We stack more attack surface. I mentioned this before. BitVM is one of the more interesting and leading technology. At least it's very researched at this point. I expect we'll see something with the garbled circuits valid implementation soon. For now, I don't know that there is anyone that have implemented on that. Big attack surface, always audit, always be secure.